how can we calculate actually cross-section and things like that when we are colliding two protons which are not point-like. The standard formalism of quantum field theory which you learn from textbooks are for point-like particles, and that is done because of a particular model of the proton which is known as the Parton model and has been experimentally verified over, let us say, last 40 years or so, could be more. So this morning's lecture will basically be Parton model. So those who are familiar with Parton model won't get much from these lectures. Number two is, in the afternoon I will show actual calculations, how we do W production, how we do W decay, and using these results how we can reconstruct particle masses. These kind of things will be discussed in the afternoon. Alright, and in the afternoon, depending on the progress, I will announce what I am going to talk about tomorrow. Okay, so it will go like that. So, but before going to the Parton model, I thought I will summarize the lecture, at least the salient points what we learned yesterday, and let me quickly go through it. Now, the first thing we learned, this would be useful for the beginners, that suppose I consider a decay. So the first important thing we learned is the concept of invariant mass, and that is, suppose this particle decays into any number of particles. Now in principle, if you square this quantity, then from relativity I know that this is going to be the mass of A, the mass of the decaying particle, and this is called the invariant mass. This is just a name. Of the n particle system. Now if these particles are visible, that is, if we know their energy and momentum, we can measure them experimentally, then this quantity can be calculated, and that obviously gives you the mass of the decaying particle. This was very essential in the discovery of the Higgs boson, as we saw. And the second thing is, in actual practice, however, the square of this quantity will not be constant. Instead, we will see distribution like this. So this is the invariant mass distribution. So I am plotting the invariant mass along the x-axis, and the y-axis is the number of events. And what we will see in actual practice is, indeed, this distribution has a peak at the mass, but this comes also with a width. There is a definition of width, but let me not go into the big definition. This is just obvious from common sense that we have to make some measurement, right? Like, full width at half maxima or some such definition. Actual definition is complicated. So this invariant mass distribution in practice calculates not only the mass of the decaying particle, but also its decay width, total decay width. If it decays into different channels, sum of the partial widths, and that is the usefulness of this plot. The second important thing we learned is the formula for total One is the number of signal events, and this is, as I told you, this is the cross section for the production of the signal. If you are interested in number of Higgs coming from Higgs production and Higgs decay, then this is the Higgs cross section. This is the branching ratio of Higgs decaying into a particular final state F. F, for example, could be 2 photons. But important quantity is this, and this you can call it as the efficiency of selection. That is, as I told you, that you will always have similar events from the background. So for distinguish between the signal and the background, you have to make some kinematical selections. For example, you can say that I will collect only those final states in which the particles come with high PT. Okay. Or we will collect only those final state particles whose invariant mass lies in a certain range. Now these are the selection criteria which is used. And Li of course is the integrated luminosity. Roughly speaking, you can say that this gives you the number of collisions over a time interval. And then you can write a similar quantity for the background. So I am not writing the formula again. So number of background will be the production cross section of the background. Then the branching ratio to the same final state. That is the standard model process, which is the background of the noise, can also give you the same final state F. And then that probability, and then efficiency of the background using of course the same selection criteria, otherwise it doesn't make any sense. That is, if you say that I want PT of the highest momentum particle to be greater than 50, then you should require this both for the signal as well as for the background, and that will give you an efficiency. Obviously the efficiency is always less than 1 because you will be rejecting certain events coming here. And then Li is the integrated luminosity, as I told you. So the question then is that the whole business of collider physics is basically optimizing this product. Li, of course, a phenomenologist cannot do much because that is decided by the properties of the accelerator. So you have to take whatever you have gotten from CERN or from Fermilab or wherever you are applying. But your main thing is optimizing the product so that, now let me give it a name. So let me call it sigma effective. That is, this is like an effective cross section, not the cross section which you calculate quantum mechanically, but the product of these three. And the whole business of colliding physics is sigma S branching ratio F, or sorry, sigma effective of the signal is greater than sigma effective of the background, such that the number of signal event divided by the number of background event is, if it is more than 5, you will be very happy. If not, at least 5. Now, if you work this out in a probability theory, then what you learn is that this greater than 5 means most probably, maybe Sanjeev or Arun Nayak can correct me. It means that at 98% level of confidence you can say that your signal is not a fluctuation. 98, is that number correct?
It is square.
Huh?
It is square.
Oh, sorry. But does this 5 correspond to 98%? I have forgotten.
No, sir. 5 sigma 99.9.
99 point, yes please. Louder.
99.9 at least.
9, no.
5 sigma. It's 5 sigma. Sorry.
99.9 is too optimistic. No. Otherwise, wouldn't require greater than or equal to 5 sigma. If you have 99.9% confidence in your result, then you wouldn't.
Definitely is 99.
99 maybe. 98 or 99.
99.
99 point something. Alright.
7.3 or something.
Alright. So, this is more or less the thing, but you have to keep in mind that typically sigma s is smaller than sigma background. Well, one reason is you are interested in producing heavy particles for new particle search. Alright? New particle search, you are not going to produce something which has a mass of a typical quark or typical lepton or anything. And of course, if cross section is calculated for a higher mass particle, then it will fall. Now this you can understand qualitatively, because when we did calculation in the last class, it was a two-line calculation. Nevertheless, it showed us that the center of mass energy should be more than mass of particle A and mass of particle B. That is, if the center of mass energy is less than that, you wouldn't produce anything. Now if it is marginally more, you will probably produce A and B, but the probability of production will be very small. This in fact is called phase space suppression, but let me not go into all that thing. So the point is, if you are trying to produce heavy particle, the heavy with respect to what? With respect to the available center of mass energy of the colliding particles. Then the cross section will typically be small, whereas in standard model processes, you will produce relatively light particles all the time, and therefore the cross section will typically be large. Branching ratio, again it's a question of choice, because both the things will necessarily be less than 1, but depending on the signal, the branching ratio depends. So your main handle is the efficiency. The main business of collider physics is look for interesting physics for which signal is as large as
Sigma B.
Well, it will not be as large as sigma B, but as close to sigma B as possible. In fact, a good idea is to optimize the product. Sigma times branching ratio is close for signal and background, and then you optimize the efficiency to get this significance.
So for phenomenologists, even the sigma s and branching ratios, these are now typically more or less, settled, not too much, their room, but the sigma s, this efficiency is the place
is the
where
main handle
where phenomenologists can give lot of inputs, basically selection, having proper.
Well, I mean, except for the fact that again this is determined by the new particle mass. So phenomenologist will try his best, but he has to do it by assuming certain mass, right? If unfortunately, if your calculation based on a certain mass is not realistic, the actual mass is larger, then of course it will fail. But anyway, that is the best you can do. Assume some mass for the new particle, or in other words, try to optimize this S by root. And then if you do not see it, then you can put a limit on the cross section or cross section times branching ratio or whatever. So this is the main phenomenology at any colliders. Now next we started with a question that protons are not point-like, right? Even undergraduates know it because we talk about the charge radius of the proton and so on. So all the cross-section formula is, so we need to know the cross-section.
So I have one question before you go to this topic. So when you mentioned about optimizing the sigma S, sigma B, we can have two scenarios. For instance, in one case background is already very high number,
Yes.
and then signal is just a, just barely crossing the fluctuation of that background. Okay. Another situation you can think of where that channel is background free almost. Okay.
Okay.
And
Yes.
you have signal.
Yes. Very good. Very good. Very good. There, it is basically a choice. Some people say that if it is completely background free, then 5 event is good. Somebody want to be more conservative and say that 5 event could be not adequate. Let us go for 10 background free events. I am not aware of any rigorous statistical analysis when the signal is zero. For low, when the background is zero. For low background, you still have computer programs which helps you to calculate the significance. S by root B does not work if the background is extremely low. Okay, because you can see that if there is one background event, then obviously the denominator is 1. But one background event can fluctuate to 4. Right?
So then should we go for Poisson statistic, for Poissonian chi-square?
You should go for available programs in the market which helps you to calculate the efficiency when you have a low background situation. Okay. Suppose you see 10 signal events and 3 background, or Y3, even 12 background. Even then, calculating the significance by this S by root B could be dangerous. It would give you wrong information. So there are available computer programs, you have to set them up. They are of course written by experts. And then you can calculate.
Sir, so this is regarding calculation, but experimentally,
Also, sir, another one way you interpret when the background is zero, that for example you get signal 10 events. So what is the propagation this 10 will be compatible with 0 between three signals?
Yes, that is also possible.
so experimentally, if you have high background, then you can really have a very good that background line estimate, because experiment is seeing those events, so you know that background line very well. So that can be advantageous. And another situation where you don't have background, basically. So experimentally, which scenario is like, you prefer the most?
No, I think it's a personal choice.
Both.
It is a personal choice. I would say that if I can make background as low as possible, I will feel more comfortable. On the other hand, some people can say that if you have a low background, then you use the formalism for computing the significance.